Hi, welcome back. In this set of lectures, we're talking about processes that are path dependent. And to describe path dependence, what I want to do is use a model. And this model is going to be based on a set of urns. These are very simple urn models. And these urn models are going to help us distinguish between processes that are path dependent and processes that are what I call fat dependent, where the order doesn't matter, but the set of things that matters. They're also going to help us distinguish between processes that have outcomes in a given period that are path dependent and processes that have equilibrium, sort of long-run distributions over the set of outcomes that are path dependent. So the outcome in a period might depend on what happened in the past. That's fine, but that's different from saying the long-run equilibrium, where the system is going to go, is going to depend on the process. So I'm going to make a distinction between path-dependent outcomes and path-dependent equilibrium. And I'm going to do this just using this very simple class of urn models. So what is an urn model? An urn model is really simple. You've just got an urn, it contains blue balls and it contains red balls, and you pick balls out of the urn. So I might reach in this urn and I might pick out a red ball. That's it. And then there's the probability of picking out balls of different color. So the simplest urn model is called the Bernoulli model, and that works as follows. You've just got a fixed number of balls in the urn. So this urn has 3 red balls and 1 blue ball. The probability of picking out a red ball is 3/4. So if you think about this, this model can be used to explain a lot of casino games like roulette and blackjack. You can think, what are the odds of getting a face card? And you can think there's 52 cards in the deck, and 16 of those cards are face cards. So there's a 16/52 chance that you're going to get a face card. So that's it. So the Bernoulli models are really simple. Probabilities stay fixed, and the probability in each draw in a Bernoulli model is independent. So if I get a red ball this time, put that ball back in the urn, that doesn't have any effect on the probability of getting a red ball in the next period. So when you say something's independent, it means what happens now doesn't depend in any way on what happened in the past. What we want to do is take this simple idea of an urn model and use it to construct some path-dependent processes. And the most famous path-dependent process is called the Polya process. And here's how it works. Start with an urn with 2 balls, one red, one blue. You pick a ball. So maybe I pick the red ball out. After you pick that ball, you look at it, see its color, and then you put in another ball of that same color. Then you do it again. So maybe the next time I pick another ball out, and again it's red, so I add another red ball. Well, then maybe the next time I pick a blue ball out, and they added a ball that's blue. Now, if we think about this Polya process, what's going to happen is that over time, these probabilities are going to change. So if we think about the Polya process in action, what's going to happen is we're going to get lots and lots of balls in here, lots of red balls, lots of blue balls, depending on what I pick out, and the probability of balls of the different colors in the ball is going to change. So it's going to start out that the probability of red balls is 1/2. Then it might go to 2/3 as I pick another one. Then it might go to 3/4 if I pick another red ball. But then if I pick a blue ball, it's going to go to 3/5. So what we see is the probability of picking a red ball is going to change over time, and it's going to be path dependent. It's going to depend on the path of previous choices. So what I'd like to do now is state 2 results about the Polya process. Now, I'm not going to prove them. In the next lecture, I'll prove why they're true. In between this lecture and the next lecture, what I'd like you to do is see if you can figure out why they're the case. So do some examples with, just with picking 3 balls from the urn or 4 balls from the urn, just 4 sequences along the path, and see if you can see why these are true. So here's the first result, and it's sort of surprising. The first result is any probability of red balls and blue balls is in equilibrium in the long run. So you can end up with 60% red balls, you can end up with 4% red balls, you can end up with 99% red balls. Any one of those things could happen, and they're all equally likely. So you're equally likely to get 4% red balls or 85% red balls. That's amazing. And it turns out it's not very hard to prove, so I want you to see if you can figure out why it's the case. Let me talk about why this is important, though, in terms of the Polya process, and also just sort of why the Polya process is important. So let's think of the Polya process as a model of fashion, let's say. So suppose that there's 2 different colored shirts you might buy. You might buy a red shirt or a blue shirt. And so you look in the store window and you see one red, one blue, and you're not sure what to do, so maybe you choose red. Well, now your friend's going to come buy a shirt, and she looks and she thinks, well, I see 1 red and 1 blue in the store window, but I see that my friend bought a red. So she sees 2 red and 1 blue, and so maybe her probability of buying a red shirt is 2/3 because she sees more red than blue. So then she buys a red. So now somebody else comes in and they buy a shirt, and they're thinking, okay, what's more popular, red or blue? And they see 3 people buying red and 1 person buying blue. And so if they're 3 times as likely to buy red or blue, what you're getting is a Polya type process. Now, what's interesting about this is that if people make decisions in that way, what this result tells us is anything could happen, and anything is equally likely, whereas likely to end up with 4% red shirts is 99% red shirts. We could use the same model to think about people buying Macintosh computers or IBM machines, right? Whether you use DOS or Mac. And the thing is, if you think about using, the probability you buy a Mac machine is proportional to the number of people who bought Mac machines in the past, you're going to get a Polya type process. So what plays out, what happens in reality, is going to be very contingent on the history, and anything could happen. So that's result 1. See if you can figure out why it's true. Here's result 2. Result 2 is that any sequence of events that has R red balls and B blue balls is equally likely. So if I get red, 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 blue, that is the same probability of happening as drawing out blue, red, red, red. Why is that the case? Again, do some examples, see if you can figure it out. I'll prove it in the next lecture. So what this means, and the reason this is interesting, is it basically says if you know the frequency of red and blue balls, that doesn't tell you really anything about the order. So if you just see the set of things that happened, you can't infer anything about the order because any order is equally likely. So again, that's sort of surprising. Let me move on to another process. This next process is called the balancing process, and it's sort of the inverse of the Polya process. In the balancing process, again, we have an urn. There's a red ball and a blue ball. But the difference here is when I pick a ball out, let's suppose I pick a red ball, what I do is I add a ball of the opposite color. So if I pick out a red ball, I add a blue ball. Well, think about what this process is going to do. Suppose I pick a red ball, I add a blue ball. Suppose I pick another red ball, add another blue ball. Well, now it becomes incredibly likely I'm going to pick a blue ball. So if I pick a blue ball, then I add a red ball. We can see is this process is going to balance itself out. So the balancing process in the long run is going to end up with 50% red balls and 50% blue balls. Now again, you could say, okay, this is balls and urn. Where does this apply to the real world? Well, it applies to situations where you want to keep different constituencies happy. So let's suppose political conventions in the United States. You might be deciding, should we put it in a northern state or a southern state? Well, if you put it in a northern state, what you're doing is increasing the probability you'll put it in a southern state 4 years later. If you put it in a northern state again, then you're really increasing the probability you're going to put it in a southern state. So it's like you're putting in balls of the other color. Or think of the International Olympic Committee deciding where they should put the Olympic Games. Do they put it in Asia? Do they put it in North America? Do they put it in Europe? Do they put it in South America? Now you can think of balls as being 4 different colors, but as you pick balls that say Europe, as you put the Olympics in Europe twice in a row, in effect you're putting balls of the colors of the other continents into the urn, making it more likely you'll pick those. And what this tells us is that you're going to end up with equal probabilities of the different continents, or in the case of the northern and southern states, equal likelihood of putting the convention in the north or in the south. So here's what we get, and this is sort of interesting. In the Polya process, we could put in balls of the same color. What we got is that anything could happen. We could get any probability between 0 and 1, and they were all equally likely. So you're just as likely to get 99% as 4%, as 60%, as 33%. In the balancing process, the only thing you can get is 50%. You get an even mix. So the Polya process has the equilibrium is incredibly path dependent. In the balancing process, it's not at all. So that's a distinction I want to highlight. You might want to make a distinction between the period outcomes, what happens in a particular period, versus in the long run, what does the distribution of balls in the urn look like? So when you think about path dependence, we can think of it either in terms of these outcomes, or we can think of it in terms of the equilibria that are generated. So that's going to be an important distinction. Path-dependent outcomes just means that what happens in a period depends on what happens in the past. That's going to be true of both the Polya process and the balancing process. Path-dependent equilibrium means what happens in the long run depends on the process along the way. So if I think of the Polya process and the balancing process, the Polya process has both path-dependent equilibria and path-dependent outcomes, but the balancing process only has path-dependent outcomes. The equilibrium is always 1/2. It doesn't depend on what happened along the way. It's always going to end up with equal amounts. Now this is an incredibly important insight because it affects how we think about identifying path dependence in the real world. I'll give an example. In the balancing process, history matters at each step in time. So when I think about what's the odds of getting a blue ball in period 7, well that depends on how many blue balls I picked in periods 1 through 6. So each period's outcome depends on the past. So if I were writing a narrative, I'd say, oh boy, this really was contingent on what happened previously. However, that doesn't mean that what happens in the long run depends on the path. What happens in the long run could be completely independent of the path, like in the balancing process. So history can matter at each moment in time, but it can't matter in the long run. And so if I just tell a story that says period 7 depended on 6, 8 depended on 7, 9 depended on 8, 7, and 6, that in no way means that history was contingent. It could very well be that the equilibrium was set in stone beforehand, that the process was naturally going to go to one place. Now, what would be examples of that? Well, two examples from history might be what we call in America manifest destiny, the idea that the United States was likely to be a continent that stretched from sea to shining sea. So the history played out in particular ways, but there would be some people who argue it didn't matter what that path was. We were destined to be a country that stretched from sea to shining sea. So even though the Louisiana Purchase, particular wars, the gold rush, all those things happened in a particular sequence, some people would argue it didn't matter. Eventually, we were going to become one nation stretching from sea to sea. Another example is the railroads. People argue once the railroads were invented that they sort of built themselves. So sure, there were these people like the Carnegies and the Stanfords that laid the tracks. But the thing is, it didn't matter who those people were, and it didn't matter what order they were laid. The tracks were going to be laid connecting the cities one way or another. And it really doesn't, particular sequences, the fact that this track got laid, track section 19 is going to be connected to track section 18. So yes, each lay of each track was path dependent, but the long run outcome may not have been. The tracks were going to be where they were going to be because that's where it was economically efficient for those tracks to be laid. So again, at each moment in time, the event depends on past history, but the long run equilibrium doesn't depend on history. Now, remember when we talk about path dependence, we're saying the outcome probabilities depend on the sequence of past events, past outcomes. I want to make a distinction between that. Remember, we have that path dependence and fat dependence, where outcome probabilities depend on past outcomes, but not their order. So I call this fat because, remember, I could think of path and rearrange the letters to get fat, by just switching the H over here. Now, I also do this because fat is sort of a little bit of a joke about thick description, right? So fat means thick, and thick descriptive accounts take into account the full sequence. The POIA process is fat. It's not path. And the reason why is all that matters is the set of outcomes. If I had red, red, blue, that means I've added 2 red balls and 1 blue ball. And if I had blue, red, red, that also means I've added 1 blue ball and 2 red balls. So all that matters is the set of outcomes, not the sequence. Why is this so important? Why do we care about it being path dependent versus fat dependent? Well, let's do just a tiny bit of math and see why. How many different paths are there? Let's suppose I pick 30 periods. And I want to know how many different paths are there. Well, there's 2 things I could have picked the first period, red or blue. 2 I could have picked the next period. 2 I could have picked the third period, and so on. So there's 2 times 2 times 2 times 2 times 2, 30 times different histories. That creates over 1 billion different histories, different paths. If I want to know how many sets there are, well, I could have added 0 blue balls, I could have added 1, I could have added 2, I could have added 3, up to 30. So there's 31 sets. So there's 1 billion paths and only 31 sets. So if something's set dependent, that means that in round 31, that means there's only 31 different possibilities that matter. If it's path dependent, that means there's 1 billion possibilities that matter. Now this raises 2 questions. First up, could something actually be path dependent? Is there something that could depend on all these billion different paths? And then second, if there is one, can I construct one using my simple Urn model? Well, the answer to both questions is yes, you can. So here's the simple process using the Urn model. It's called the sway process. And it's going to give us a really interesting insight. So the sway process works as follows. I start with 1 blue and 1 red ball. When I pick a ball out, I add a ball of that same color, just like the POIA process. But I also add 2t minus s minus 2t minus s minus 1 balls of the ball chosen in each period s less than t. What does that mean? It's complicated. Let me explain it with a picture. It makes a lot more sense. So in period 1, I pick a blue ball, I add a blue ball. In period 2, I pick a red ball, so I add a red ball. But then I also add a blue ball for the blue ball that I picked in period 1. Period 3, let's suppose I pick a blue ball, so I add a red ball, again, for the red ball I picked in period 2. And now I add 2 blue balls, so multiplying times 2 the blue ball that I picked in period 1. Period 4, suppose I get a red ball. Now I add a red ball. I add a blue ball for period 3. I add 2 red balls for period 2. And I add 4, or 2 times 2, blue balls for period 1. So what happens is, for each ball that I pick, I'm adding 1, then 2, then 4, then 8, then 16, then 32 as I move through time. That's why I call this the sway, because as you go back in time, decisions take on more and more weight. This is really interesting, because what's creating this full path dependence? It's the path taking on more and more influence. So when people talk about path dependence, when they give examples of the law, when they talk about institutional choices, when they talk about technological adoptions, they often talk about early movers having a bigger effect, and the past really sort of having increasing weight. What turns out, one way you can get full path dependence is by having exactly that sort of process, by having the past take on exponentially more weight over time. So that's really interesting. Very simple Urn model has told us how something we had some loose intuition about. For something really to depend on full history, not just on the set, you've got to have the early path take on more and more weight over time. Or at least that's one way in which you can get full path dependence. All right, I realize there's a lot going on here, but here's what's really interesting and it's really useful. We take a really simple class of models based on urns, just these really simple urn models. From those urn models, we learned some interesting things. We learned how to construct a very simple path-dependent process called the Poyer process. We constructed something called the balancing process, which showed us that you can have path-dependent outcomes in each period, but not have path-dependent equilibrium. You can go to a particular thing each time. And then we even constructed something called the sway process that gives us full path dependence. And that showed us that one way you can get full path dependence, and not just fat dependence, is by having the weight of history increase over time, which is something intuitively I think that a lot of historians and a lot of scholars of technology have felt was true. And this sort of shows us why, in fact, that may be the case. Why, when we see something that seems really contingent, it might be the case that what happened early on had a larger effect. Okay, thank you.